Okay, Calc BC lesson 7.6. Honestly, one of the longest lessons of our entire school year. I'm going to try to streamline it some. You can see at the top, I've sketched out graphs of sine, cosine, and tangent. Very quickly, you might remember that we really need to have a one-to-one function to be able to find an inverse. A one-to-one function is one that will pass the horizontal line test. Sine and cosine both will fail, but if you look in yellow on the sine wave from negative pi over 2 to positive pi over 2 on x, we can take a little section of that would pass the horizontal line test. Similarly for the cosine of x, if we went from x equals 0 to x equals pi, that would be another section. Tangent already would pass the horizontal line test, and that would be wonderful. But look, I guess what I want to point out to you real quickly is when you're finding in an inverse, you'll always switch your x and your y values. Like if you had pi over 2 comma 1, you'll be at 1 comma pi over 2. You'd be at 0, 0. You'd still be at 0, 0. Down here, you'd be at negative 1 comma negative pi over 2. Here is a graph of the inverse sine function. And you'll notice that the angles that are coming out as your output are between negative pi over 2 and positive pi over 2. In all honesty, I think I do want to point out that this little circle right here, you might remember from your days in trig, this is actually the wonderful shortcut to help you know what the angle boundaries are for inverse sine. It's just between negative pi over 2 and positive pi over 2. For inverse cosine, we could do something very similar. Take that section in green up there, switch your x comma y's, you would get a nice inverse function. But again, more to the point, you could plain and simply just say, well, look, on a angle boundary on the unit circle, I'd be going between 0 and pi. Remember that, and you'll be in phenomenally good shape. Inverse tangent, hopefully you remember the shape of that. It almost looks a little bit like a stretched out letter S right now. You can notice that your y values, your range, are between negative pi over 2 and positive pi over 2, not equaling either of those endpoints. So inverse tangent would have angle boundaries amazingly close to what you'd see for inverse sine, just not including pi over 2 and negative pi over 2 themselves. Well, yes, this is a calculus class, but part of what we'll be seeing on our homework and actually quizzes and tests will be a little bit of review. Let's just do example 1a. The inverse sine of 2 pi over 3. Well, the sine of 2 pi over 3, that would be a 2 pi over 3 is in the second quadrant. Sine is positive there. With a reference angle of pi over 3, sine of pi over 3 is root 3 over 2. So we're really going to take the inverse sine of radical 3 over 2. But of course, this means that we're going to have our angle boundaries that we're seeing up above only between negative pi over 2 and positive pi over 2. This is a positive value inside here, so we must have an angle in the first quadrant. And that angle would be pi over 3. It's very important to note that inverse sine and sine do not just touch and cancel here, leaving us with a 2 pi over 3. For part B, let's take a look at the cosine of 4 pi over 3. Cosine of 4 pi over 3, some good old-fashioned trig review. A reference angle of pi over 3, cosine is a half, but 4 pi over 3 is in the third quadrant, and cosine is negative there, so we'll have a negative 1/2. But now we need to do inverse cosine of this negative 1/2. And as we think this through, I hope you look at the angle boundaries up above, only between 0 and pi. With a negative value of negative 1/2 here, we're going to have an angle in the second quadrant. We, of course, know already that we'll need a reference angle of pi over 3. But, of course, the final answer must be 2 pi over 3. As we continue on, just some good old-fashioned pre-calc review at this point. I guess I just want to point out that whenever you see inverse sine or inverse tangent, those are really representing angles. So this is really saying, would you find the cotangent of this angle? But the angle, of course, is a very special one. It's between pi over 2 and negative pi over 2. But because we have a negative value, it's over here somewhere. And here's my angle A. And in fact, I could even say that the sine of that angle is negative 2/5. And sine is the y-coordinate over the r-coordinate. So I could say y is equal to negative 2. The r would equal 5. And of course, I'd like to find out what x is. We can do that from the Pythagorean theorem. R squared equals x squared plus y squared. We'd have 5 squared equals x squared plus negative 2 squared. Well, here we get 25 is equal to x squared plus 4. Subtract a 4, we have x squared is equal to 21. You can see in this quadrant here, x is moving to the right. We will just choose a positive radical 21. Now, if the tangent of an angle, remembering our trig, is the y-coordinate divided by the x-coordinate, cotangent is the reciprocal. It's simply the x-coordinate all over the y, meaning we will be left with radical 21 all over negative 2. And of course, that would leave us just pulling that negative out in front with a negative radical 21 over 2. For part B, a very, very, very similar kind of a setup. We're really saying find the secant of some angle. It's not just any angle, of course. It's an angle for which the tangent of that would have a value of 7 over 4. And tangent, of course, is going to come into play in one of these two quadrants. Inverse tangent is always between negative pi over 2 and positive pi over 2. Because everything is positive here, will be in the first quadrant. And tangent, like we were just mentioning, is really y all over x. So x is 4, y is 7. We're left to find our r. So r squared is going to be y squared plus x squared. And without too much work, you'll see 7 squared plus 4 squared. That's 49 plus 16. And just adding that all up, you should get 65. R, of course, is a distance, so we'll always choose the positive radical here. And secant, well, secant is the reciprocal of cosine. Cosine is x over r. Secant then is r over x. Plain and simply, we will have radical 65 all over 4, and we'll be done. As we move on, though, assuming that x is positive, find the sine of the inverse tangent of x. We're again looking at the sine of some angle. And assuming that this inside x is positive, that would indicate that our tangent has a positive value. Tangent of this angle is x over 1. Remember, tangent was always the y-coordinate over the x-coordinate. You could even say it's opposite over adjacent if you'd like. And then we'll try to find our r. Let's see, we'll say r squared is equal to x squared plus 1 squared. And without too much work, we're going to be able to take a square root and get radical x squared plus 1. Now, of course, just remembering that sine is always your y-coordinate over your r, or its opposite over hypotenuse. Regardless of how you're looking at it, you'll get the same value, x all over the square root of x squared plus 1. Okay, as we move over here, very, very, very important for us to talk about the derivatives of these inverse trig functions. Ordinarily, I would do at least one of these proofs. That being said, we're very much pressed for time. So just in case you'd like to see the proof, you can look in the book, or you can ask me in class, and I'd be happy to help you out. But the derivative of the inverse sine of u is going to be 1 over the square root of 1 minus u squared. The derivative for inverse cosine, it's going to look exactly like what we just did. One huge difference, though, there's a negative out in front. The derivative for inverse tangent, 1 over 1 plus u squared. The du dx then means take the derivative of the inside. Perhaps the strangest of the inverse trig derivatives, the derivative of inverse secant, is 1 over u times the square root of u squared minus 1, then multiply by the derivative of that inside. So, with no further ado, let's jump in and take a peek at the derivative of inverse sine. Looking at the top of the screen, I hope we can quickly follow the pattern. We're going to have 1 over the square root of 1 minus, now u is the argument, it's whatever's inside here, so that's your radical x squared. But then we have to take the derivative of the inside. And I hope we've done this enough for you to fondly remember that the derivative of radical x is 1 over 2 rad x. So, of course, you could go through and prove that, writing that as x to the 1/2 and work that all out. But suffice it to say, as you clean this up, there will be a 2 out in front. You can put your radical x out over here. But then we've got this big square root, and we just have 1 minus an x. Because when we square this inside part, radical x squared goes away. What we're probably going to do then is multiply that radical x back inside. Or you could even just move it back inside just so that you have 1 radical as opposed to 2. Another way that you might see this written would be to have the x factored out, just as so. Okay, as we take a look at example 5, as we take this derivative, we're going to use the chain rule. We're going to bring that 3 down. We'll say 1 plus inverse cosine of 3x, and now we'll have a second power. And then we have to take the derivative of the inside. The derivative of 1, of course, is just 0. But let's remember what the derivative of inverse cosine is. It looks just like inverse sine, but there's going to be a negative. And in fact, you could put that -1 up in front. So let's say -1. Here's our square root of 1 minus. Here's my argument of 3x. I'm going to have to square that. But now I'm going to say, well, what's the derivative of the inside? The derivative of 3x is simply a 3. And just cleaning this up a little bit, I hope you'll notice we have a 3 and another 3. That would multiply to a 9. We also have a negative, so I'm going to have a -9. Then I'll have my 1 plus inverse cosine of 3x, whole thing squared. And down below, you could square on the inside of this radical if you'd like. 3x quantity squared actually becomes a 9x squared. And that's how we do a problem like example 5. It looks like we're running out of time. We're going to have to continue to take some derivatives, and then we're going to move on to taking some integrals.